So we started at the end of my lecture, I started doing what is that called? Uncapacitated facility location problem. And so basically for facility location problem, we are given some set of facilities, set of clients, there's some opening cost, and if a particular facility serves some client, how much cost the client has to pay. And the objective is to come up with a set X subset of facility, that set of facility that you want to open. And the moment you open some set of facility, you assign every client to the closest facility it is available in the X. Okay? And what is my overall objective is to come up with an assignment or come up with a set X such that this cost is as low as possible. And what is the cost of a set X? Okay, opening cost plus what is the cost for assignment? What is the cost every client is paying for the facilities that it serves? So if whichever facility serves, it pays this much amount of distance or money or whatever you want to. So we want to do this. And what we saw last time.
It is not 11:45?
No. At least last class I made it very clear.
So it will be 11:30 every day?
Till I don't change it. I told you it was changed because of lock-ins constraint. Okay, but like otherwise I wrote 11:30s. So maybe when lock-in start teaching next semester, like next month or so, then we'll change the time, but not now. Okay, otherwise the class will become a little bit later. Okay, but that's okay. Okay. So we saw that we can model these things as following set cover problem, where you have a universe for set of clients, and for every facility and a subset of client, I have a set in my set cover with some C prime. And what is the weight of that set if you pick this? It is this. You understood this point? Okay. Now, so we saw that the problem with this set cover formulation was that the family size exponential, and we do so we cannot just explicitly take this and translate it into a set cover instance, right? Because then that's already quite a lot of time taking. So I'm going to give you a greedy algorithm which basically tries to, so as I was trying to tell you yesterday when I was trying to explain my algorithm, is that at any point of time my algorithm is going to contain some initially X is empty set, D subset of C is already served clients or already set of clients that I have already decided to serve, right? I have already decided, and so these are the two things. So our idea was that, like, okay, fine. So at any point of time, I'm trying to serve a set of clients. Okay. So ultimate goal as the set cover is to covered my set of clients. Okay. So at some point of time, I have covered some set of clients. Okay. I have covered some set of clients. So if we were doing a set cover algorithm, what will we do? We generally do is the following: we pick up a most cost effective set, most cost effective set, which is like most cost effective set that covers uncovered elements, right? And then we try to greedily put that, right? So that is what our algorithm does, right? So now what is the definition of greedily, like, so basically if you notice is that then what is that? So basically then it will be that I have to pick a set, and what is the definition of cost effective set? The cost effective set, you are going to pick up some C prime, some I and F you are going to pick up, right? Something, okay? So suppose you choose some I and Y subset of C minus D. So Y is set of uncovered this thing. I decided that I will open up a facility at I and this. So what is the cost effective set corresponding to I and Y is going to be weight Fi plus summation j in Y, right, D of I comma j. The client j is served by this divided by the payment Y's. So per client is going to pay this much amount of cost. Okay. But I noticed, I told you that my sigma has a property that it must assign every client to the closest facility that it is open. So, in the beginning, I am also maintaining a sigma from where D to currently opened X. Okay? But now notice that if I decide to pick up I, now my X becomes what? X union I. Okay? And D will become D union Y. Okay? But now notice that it's possible that now that some facility I has been opened, some of the clients, the closest distance is to I, not to the whatever they were assigned previously, right? So maybe previously they were assigned to some J, but now they are assigned I. So but now what is the cost? Like they all were paying certain amount of cost. Okay, now there is a cost reduction. You understand the point? There is a cost reduction. So how do I get that in? So this is what we define. That we define given a set D and a facility I. Okay, say and a facility I. What is the change? What is the change if the clients in D is assigned to I? And what we said is that okay, if someone is already to its closest, it will not like to change its, right. So this is why we define this notion of delta D comma I, which was summation over, I said max 0, which was to signify that they may not like to change, right. Why will they not like to change? Because now they are costing much more than what was costing before. So max of this, okay, J in D. So before it was assigned to which one? Sigma of J, and now it is assigned to I comma J, right. So whichever is cost, I take extra, right. So what I am saying, if this quantity, when is this quantity negative? When assigning to I is more expensive, then let us not assign him, right, because that is why, right. And when it is good for him, when wherever he was assigned, now where he is assigned, right, if the cost is the reduction. So this is what, so whatever happens, if I have taken I, this is a change in cost that will happen. Okay. So I said let me subtract this, okay, subtract this, okay, subtract this. So these are the kind of cost effective sets that we will be talking about. Okay. Now given this notion of cost effective sets, how I am going to write my algorithm? Let me write my algorithm and then we will try to see how to implement that algorithm. Okay. But one more thing that I would like to allow myself is that notice at some point of time it might be that there are some set of elements here, okay, some set of elements here, who says here, okay, that I need to assign. Okay. Is it always a good idea to allow new facility to open, or I said okay, rather than opening a new facility, let them assign it to already open facility, because you understand? Yes.
So here you wrote minus delta of D comma I.
Yes.
So the only facility which you are opening is capital Y. So should it be delta of capital Y comma I, or
Y is not a facility.
D comma I?
Y is not a facility. Y is a set of clients.
Yeah.
No, but C
Oh,
minus
set of clients. Yeah. Okay. Oh.
Set of newly chosen clients, C minus D. Y is subset of C minus D.
Yeah. So delta of D comma I, it should be delta of Y comma I or D comma I? That is my question.
Think
Here,
about it.
The formula you wrote.
What is Y? What is Y?
Y is the new set of clients whom you are going to serve in this iteration.
That's right. But while serving this iteration, I opened a new facility which reduces the cost of already existing clients.
but Y is not taking
Oh,
anything
okay,
from
yeah,
D.
yeah.
That is why it is already existing car. right? That's it. But what I'm saying to you is that we also should consider that at some point of time, maybe there are some set of guys which has come now. Maybe they are better served by opening, like using it to go somewhere else. Why? Because maybe opening a new facility is very expensive, right? So I have served my customers, clients, and now some set of customers are very few or something is left that it might like, so the most cost effective thing could be is rather than opening a new client, just assign it to the already existing clients, right? So at every iteration, I should allow that possibility to happen, that hey, is there some subset of clients for whom, right? Because for those subset of clients, this cost is not there because already is, right? So all he needs is the cost to go there. So I allow both kind of things to happen during my algorithm, right? I allow my algorithm to have full freedom, right? You choose whatever you feel like.
Why can't you put this decrease minus that increase? Means this is decreasing, but
Plus
those
Fi.
opening sum over fi that I am adding, that is also increasing. That division. Why
That is why here, no? Opening cost.
problem? We are considering everything.
No, but I'm saying I also allow that some subset of clients are served by someone before, already open guy, rather than opening a new guy at every iteration.
Considering it anywhere, those things.
I have not yet written the algorithm, no? No, so what is your question?
You said that you were keeping that freedom. Means
Yes.
what?
I will allow a set Y to be chosen outside and being served by already existing facility without opening a new facility. Okay? So imagine that this some guy was already doing this. I said, okay, hey, you do not only do this, you also serve these people. That's all that I'm saying. And I'm allowing that because now what happens? I have already served some clients. I'm saying, okay, for these new clients, rather than opening a new facilities, let me assign it to already existing facility. I want to allow my algorithm to have that kind of freedom, right? Because in the beginning, these were, when I was looking with J and this, it was not the best set, right? It was not the most cost effective set. But later, for some subset here, the most cost effective way is to assign someone else rather than doing some Fi. So I will allow both possibilities, right? But I will allow what happens if I don't open, what happens if I open up someone new. Okay?
When we choose the facility, we are choosing it arbitrarily.
No, I choose among all the sets, I choose which is the most cost effective set. That's all that I'm doing, right? I'm not choosing arbitrarily. I go over all these sets, which is exponential, and I will tell you in a minute how to do it in polynomial time, okay? And I pick up the set as exactly like my set cover algorithm, which is most cost effective. Okay? Okay, so I have explained you what it is. So this is how my algorithm looks like. Okay, so it takes as input F, C, and D. Okay. Initially, X and D is assigned empty set, and sigma function is assigned to some bot. Okay. So while D is not equal to C, while not all the clients are served, what I'm going to do? Pick a facility I and set of unassigned clients Y, subset of C minus D, so as to minimize. Okay, and what is I want to minimize is the following constraint. minimize you will understand what I mean. Okay, so let me explain this algorithm to you. Okay. Okay. So algorithm is exactly the same which I've been trying to explain from that point of time. Is that so? I pick a facility I, okay, and I choose a facility I and a set of unassigned clients so as to minimize this function. What is the minimize this function? What is 0 I in x means? Look, if I'm going to choose a facility I which is already selected, then this cost is 0. So that is 0 if I is in x. Like x is already selected facility. So I'm saying if I'm choosing y and decide to map it to someone else already selected, then this cost is 0, right? Else this cost is equal to 1. You understand? If I'm using already existing facility, then this cost is 0 and then everything remains. If it is a new facility, then 0 I on x becomes 1. So this is just a function. Think of this as a function, right? So if I belongs to x, then this function takes 0. If I does not belong to x, then this function takes 1. So this is basically a notation and this. Okay. Now what I do, then I assign x to x union I, d to d union y, means this is a facility. So if I belongs to x, then x remains x. If I does not, then it became, and d union u is a newly set of new. And what I do for all j in u d prime, we assign sigma j to y. So everybody in y gets assigned to I, okay. And what is d prime? D prime is basically these people. So d prime is subset of d that needs reassignment. Understand? Right? Not every client needs to change its partner or needs to change its facility. So d prime is precisely those clients that needs to change its facilities. Okay? So this is so for all those, if this is the max, then that belongs to d prime. Okay? So that's my overall algorithm. Okay? That's it. Right? So if you notice, I have used in my defining my cost function here, I have used my ideas from facility location, but algorithm per se is basically a set cover algorithm, right, which tries to find a sets from here. Now you might see, why did I do this, right? Why did I allow this? If you notice in a set cover, I was saying, oh, allow him to pick 2 sets, 3 sets of the same I, which I said, look at this I and let's group them together. Remember I said, pick up this I, and suppose first time I picked it up set, I was assigning this, then I said, okay, then let's get another I and put all these clients as a part of my proof, right? So this is what I'm allowing this greedy algorithm to do, right? But I know that if greedy algorithm picks I comma this set, actually he is paying even less because at that time he doesn't need to open the facility, right? So I have incorporated what I did in my reduction as part of my algorithm. That if imagine that I chose some I, so if I chose some Fi C1 and then later I decide to choose Fi C2 in my greedy algorithm, then what I did, I said, hey, then let's do one thing, no, Fi C1 union C2, right? So to, like I said, okay, but greedy algorithm could do this, so let me allow greedy algorithm even better, that okay, next time if you pick up something, then actually you don't even have to pay for this. So might be if that is better for you with respect to cost effectiveness, do that. You understand, right? So I'm allowing my algorithm exactly whatever greedy could do and whatever proof allowed us to do, I'm just giving that power back to the algorithm to utilize it. You understand? Okay. So that is why I'm allowing this power of, because ultimately I'm running a set cover algorithm in my head, right? Analysis and everything could be very different and challenging task, but in the head I'm trying to run and this. Okay. So if I have to do this, there are 3 steps that I told you. One, we have to come up with a charging scheme. Okay. So the sum of the charge equal to total cost. Okay. Okay. And then for every set, I said total charge, the like weight of the charges in any set is not too far away from the weight of the charge, like weight of the set. That's it. So I have to come up with these 2 steps, and then if I'm able to establish these 2 steps, I will be very happy. So let's try to do that.
I have one small doubt that we are choosing Y set of unassigned clients, right? So first D is phi, like empty set. So then the total set will be C. Like how we are choosing?
How do you know? What do you mean? I wrote all these sets. Which is the most cost effective set? Who told you that most cost effective set will be this?
Okay, Y is the most cost effective set.
I have written the definition, no?
No, this is phi of
Read the definition, no? It has in the beginning, so you will put this cost. There is nothing, so this is 0. What is this? Weight of that set divided by. Yes, pick a facility I and say, so as to minimize this function.
So I and Y both we are choosing in that.
I am choosing I and Y such that this function is minimized. I am not choosing this any arbitrarily. So there are several questions and several steps. First, how do we choose I and Y? That's a one thing we'll worry about. I'm not going to tell you how to do it now, but this can be done in polytime, and I have taught it how to do it in polytime actually. Okay, so I can find I, Y minimizing this function in polynomial time. Okay, okay. We'll come back to this discussion at the end. Okay, okay.
Sir, I have a doubt.
Please ask.
So when zero of I belongs to X is 0 at some point of time in the algorithm, like it means I was picked before, and this time you are including more clients to the same facility.
That's right.
Because initially you did not pick these clients.
Yes.
Because initially there was a chance that these clients could be served better than this I.
Yes.
Right?
Yes.
Then how did at this point, so that better chance, how did it go away at this point of time?
I don't know. This is the most cost effective set I'm picking at any point of time.
Oh.
I have a very rigid definition what I'm going to pick. If already existing I and Y happens to be the most cost effective set, then let that be. You understand that?
Yes, sir. Yes, sir. I understand that. I was just wondering why. I mean, you would have picked the same set of clients while you were choosing facility I itself. Like, so when you were choosing facility I, you did not pick them. Imagine
yourself that after making some set of choices for some things, now that's the best choice. In the beginning, that may not have been the best choice. You understand what I'm saying? Look,
Yes,
it's at the end of the day, it's a greedy algorithm, right? Greedily, I was able to decide that, okay, what I'm trying to do every time, I'm trying to see by picking which set I can serve lot of customers with paying not lot of money. Understand the point? Or it's actually not lot. Which set, if I pick the cost per client is minimum. Okay, that's my only algorithm. At all, imagine that every client is go and pay some money, okay, to this. So now all I am trying to tell at any point, hey, which is the minimum, which set of clients that I can choose which will pay least amount of money and get included. That's all that I am trying any point of time, right? And how do I get that? I said, okay, look at the cost divided by set. That is, so if this set goes inside, these clients together pay this much money. I do not have preference over clients. All clients are just like set, right? I check this for everything. Then I say, oh, if this bundle is picked, then this is what it is. And imagine yourself that, yeah, so that can happen. So that's like, I do not understand what is your, I mean, I'm not a, I mean, maybe there are some more intuitive reason for this, but at least I have no idea. Okay, okay. So that brings us to, so let me define some sort of charging scheme based on this, and then we will go back to the analyzing thing.
Sir, here, why is not y a singleton set?
I am not, why I have never told y cannot be a singleton set.
It seems here that y being a singleton set will be helpful, because every time we are picking one, the next time we can pick it and we can assign I to it.
Imagine I opened one facility, right? This facility cost, if I open 500 people, because this is common for everybody, it might get per cost can be divided, no? Imagine yourself, 501. If it is, how much I am going to pay? 501? Now how much I am paying total? 502, but per unit cost is how much? 251. 1. You understand? So because there is an opening cost, right? So if there are more clients that it can serve, probably then this opening cost is much more what do you call what is that? Okay, equally divided, let's say. I don't know this word. Yes, egalitarian. And either way, I am not stopping it to be not singleton. Am I stopping it from singleton? Then if that happens to be most cost effective, let it be. Maybe at the end that's all that we will get. Like there are some client here, then that is the time. Imagine that, you know, you have covered many people and there are some outliers. For outliers, rather than opening at the cost, right? And that is why in the beginning those outliers will not concentrate here, because if I pick that outlier, the cost of my set becomes far too much that even if I divide, nothing happens. But at the end, now that few people are left at very, very far places, opening a cost here is too much that assigning it to someone else is.
Maybe I don't still understand when this is a y singleton. I didn't understand that.
What you did not understand?
So if y is a singleton.
I'm not saying that y cannot be singleton. Where did I say y cannot be singleton? Set of unassigned client y subset of C combined D. Where it says that y cannot be singleton? All it says that y shouldn't be empty. That's it. Okay? And I should probably write here C prime subset of C, C prime not equal to empty set. Okay? Fine. Right? And I gave her logic. Why? So what he says that, maybe this distance, so this is better, but no, you're also opening a facility here. So if I just serve these people, it is 501. But if I serve 2 people, it is 502 divided by 2. If I serve 10 people, it is 510 divided by 10. It's becoming much, much smaller, no?
When we open a facility I and we have already opened I-1 facilities, then this realignment cost we have computed for some facility. Previously, then per unit cost might change for each client.
Which client meaning? No, I am only, I'm never going back. It's not a heuristic algorithm, please guys.
But this client has now relocated to the new.
Yes. What client? Some old clients has reassigned it. Yes, fine.
Now we are computing per unit cost for that client.
No, I am not computing.
Why is paying for that?
Why is paying for it? It is not computing. Who is computing? Why? I'm saying at this point of time, look, all these things done is something, some charging scheme in my head. Let me tell you, look, ultimately I have paid some sets and paid some something, right? Whatever happens, there is some alignment has happened, there is some cost that is fixed, no? Whatever algorithm does, forget it. And my output is an x and sigma. And moment I got an x and sigma, I have a cost here. I have to tell you how this cost is equal to whatever I'm trying to do. You understand my point? But for this is just at the end, I'm going to output x and a sigma. X is a set of clients, sigma is an assignment. What is an assignment? For every client, assign it to the nearest this thing, and that's it. Okay. So for now, let's just believe that this algorithm runs in polynomial time. Okay, and let's try to do the analysis. Okay, so let's fix some notation. Okay, x star is set of facilities open by optimum solution. Okay, by optimum. Okay, and sigma star is an assignment from C to x star, right? If I know x star, sigma star is fixed because you assign for every client. So this is with respect to opt. Okay, okay, and I'm going to call let dj star. What is dj star? Is going to be what is jth client distance or contribution of its distance in the optimum. So this is like what it will be, sigma star of j comma j. Okay, and what is f star? Is fi I in x star. So this is like the optimum cost of opened, like optimum facility cost by x star. Okay, and what is c star? The cost is summation j in c dj star. Is that fine? So what is the opt? So do you agree? Opt equal to f star plus c star. Is that fine? So this is what with respect to opt. Similarly, we have something, right? So we can similarly define x sigma. This is returned by algorithm. This is returned by the algorithm. And I'm going to call what is dj is like d of sigma j and j. So what is a client paying in the our algorithm, and this is what client pays in an optimum solution. Okay. So now I can similarly define f algorithm is summation I in x fi and c, this is okay, and what is c algorithm is summation j in c dj. So what is the cost of an algorithm, right? And I'm going to call all alg equal to f alg plus c alg. Is that fine? This some notation that I have set it up. Okay, and basically what we have to relate, we have to come up with that the algorithm, okay, to show that alg is less than 2 times opt. So this is my objective at the end. Then I am able to show that this is a factor 2 approximation for my problem. If I show that the alg, which is the cost of the solution returned by my algorithm, is at most 2 times the cost of an optimum solution, then we are happy. Okay. 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 Is that fine? Now can I start to remove this? Okay. Okay. Because I want to keep the algorithm, and I hope by now you have understood the definition. So if you look at the charging trick, right? How did we do the charging trick? How was the charging trick defined in set cover algorithm? So we said the set cover algorithm, if you recall correctly, we said, okay, fine. Look at the way the elements are covered by my algorithm. So we said, okay, these are the first set of elements that are covered. This is the next set of newly elements covered. This is the next, and so on and so forth. And all these got some charge. What was the charge? Set divided by the number of elements that was covered by this set, right? And we called each of these elements, whatever that it means, we gave them alpha 1, alpha 1, alpha 1, alpha 1, okay? So, and so if I really think of a charge of an element, so if a vertex is here, if I belongs to first group, then say beta I equal to alpha 1. When an element was picked into the second thing, it was, okay, or rather let us say, I don't like beta's writing. So suppose everybody got beta 1 here, beta 2, okay, beta 2, beta 2, beta 3, so on and so forth. Now there is no alpha, but now I am defining alpha, okay. For every vertex or for every element I, alpha I equal to, what is alpha I? Ith, so I want to define what is my charge. Alpha I is equal to beta j if I is covered by jth set, right? So if this element appears in this, then that's it. So that now everybody has a charge. Is that fine? Okay. So this is how we were doing for set cover. And then what we said, I said, okay, the way we have assigned this, this value of that algorithm was alg was equal to summation alpha I, right? Is that fine? Because what is the weight of this set? Is right beta 1 times this, right? So that will be that many times alpha I will occur. What is the weight of this set? Beta, like what is it? Beta 2 times this set size, right? So this is what it is. Now I would like to do exactly the same for our purposes. Okay. Okay. So I will like to do this for our purposes. Okay. So when does it happen? Okay. So now we say, let's fix a client J. Fix a client J and consider the first iteration when it enters T. Okay. Fix a client J and consider first iteration that it enters T, right? At some point of time, elements are added to D, right? Look at the first time it enters, right? Okay, and that is the time when I am going to pay him. So the first time when it is covered, I am going to pay. So every time, look, it's possible that this set also contains some previous element, but that is not the time when he pays. He pays when you are covered. So every element, the moment I am covered, I pay for it. And what is its pay bin? Okay, so if it enters D, okay, okay, when this happens, when we chose a facility I and a subset Y. This is what when happens. okay, and chose and this can already be in X. Is that right? Okay. So when first time it enters, when you are able to, you find that Y there, which is uncovered, and some facility that you want to map it. Okay. So we assign a charge alpha j equal to, what will be assigned? Simple, right? Whatever this is. Okay. So what is it? What charge will I assign? Phi I y. That's it. So that's a charge, because ultimately what I was doing anyway, per covered cost by this set, right? So this is this charge. Okay. Notice j can be reassigned to a different facility later, but we will not modify this alpha j. You understand? Okay? Okay. So whatever this alpha j, we need to say whatever the algorithm returns is summation of charges, right? So key lemma is, okay. So this is a very static definition. If you first time enters, whatever you paid is your payment, right? Maybe later you get to pay less, but don't worry about it. Someone else will take care of that. You understand? But I take your total amount of money, what you paid now, okay? What you paid while you entered, okay? You pay less to the algorithm, someone else feels great about it, not you, right? For example, you already got benefit of this, no? At your stage. So someone else will benefit at you if your price goes down, but don't worry about it. So what is my key lemma? Key lemma is very simple. Alg is equal to F alg plus C alg j in C alpha j. That's it. Okay, right? So I'm saying total sum of charge is exactly the cost which my algorithm pays. Total sum of charges is exactly equal to the total cost that my algorithm pays. Now I can just worry about charges and how the sum of charges of a sets are related to each other, and then I will be done. Is that overall idea clear? Okay, but why is this proof? Is this proof not obvious? Okay, first of all, the way our assignment is, you are only going to, if you are going to open up some x, you are only going to pay once, right? So, right, you are only going to pay once, okay? Now notice that, and when you paid, so first of all this charges of Fi you only pay once, first time when you opened up new one, right? So how much did you pay? So you paid, suppose at the time you paid some Fi divided by y, but how many people has this charge? Y many. So this is what you paid at that time. You understand or you don't understand? Look at this charge is distributed to how many elements? Cardinality of y elements, right? So Fi by y is summed for each of these elements because they are part of alpha j, right? What is alpha j? You can think of alpha j as Fi by yi plus this, okay? So this is why, and once you charge Fi, you never charge again. So this is why this will get cancelled. So this is clear that this summation of this guy is, at least the Fi contribution is equal to F alg. Now let's try to understand the contribution of C alg. Okay. Okay. So think of the total cost that you pay in your algorithm at any point of time. Total cost. Okay. So at any point of time you decided to pick something. You decided to pick this set. How much you paid? You paid some amount of money. You paid some amount of money at that point of time for this. Next time, because what happens? You pay this into whatever set you are going to cover. right? So you basically at that point of time you will take this, but how much money should you have subtracted? How much money should you subtract? So imagine at this point of time I have this. So I ask you, okay, now what is the cost with new assignment? If I added a new I, what is the total cost? So the total cost is, whichever new people he assigns minus the reassignment cost. What is the minus reassignment cost? Is this one, and this is added by y people. So if you sum them, you are actually subtracting how much at this point of time from the total. Okay, so you had something here, say some A, now you added some value, got B, and what did you subtract? That's what you needed to subtract, so it is C. So everybody else is taking care of this. So everything that you add, so think of this way, I'm adding the costs, then, so you're basically what happens, every time a set goes, it actually just adds this amount. Every time that you add a set, right, you are actually just adding this to the total cost, because you have distributed this total cost to the new elements that you have added. So actually the total cost that at that effect is this, which is perfectly fine. I added this, there is some reduction, then so be it. So that's a current cost, right? So if I'm able to maintain a correct current cost after every iteration, then at the end, this is all that will be left. Right? So by induction, if you can prove, in the beginning we have a correct cost, after every iteration, correct cost is what is preserved here, if you sum up the cost charges. Okay? Okay? So this delta I takes care of the drop, right, at that point of time. So everybody pays, but like drop, when drop happens, those elements gets a benefit out of it, right? By how? Everybody is, okay, I said, actually you should have paid this, but someone has already paid for you, don't worry about it. So you pay a little less. Think of this way. So at this happens, someone already paid for you. Now you pay a little less. Each of you pay a little less. Okay, so I took care of the payment already. Now this is just very simple. Okay, next when I came, I say, hey, somebody already took care of you. You have to pay this much, but someone already has paid a lot of money, so I will charge you a little less. So I have charged you a little less. That's it. That is why if you sum them, it's the sum of the charges. It is just a simple mechanism. Okay. Once the key lemma is established, once this is that charges is equal to the cost, now I can think about the charges. Okay. So what are my sets here? What are my sets here? My sets are some f I c. So if I have a following key lemma, which says the following lemma, okay, for any facility I, and any subset Z, subset of C of clients. Okay. So if I fix a facility and I fix a subset of clients, I get a set, right? So what I want to say, okay, okay, let me, this is useless, or maybe even, so is this notation clear to you people? Can I rub this? Have you written, if you're not, take a picture because you might need it. Okay, so I'm going to rub it. Is that fine? Okay. So now I want to say, okay, fine. So these are my potential sets. Now I want to, what I want to, as I told you, right, I want to understand what is the sum of charges in this set relate to the cost of this set. That's my goal. Okay. So what will arrive? Summation j in z alpha j. if I show that this total is less than what the cost, I am going to show that actually I have fixed facility I, right, and it is actually less than some Fi plus, if I show that this is less than equal to 2 times distance summation j in z distance from I comma j. Is that fine? I want to show this. You understand what I said? So I am going to show this lemma. Okay. What is the cost of this set? Please tell me, is this not the cost of set? If I forget 2, is this the cost of the set? What is the cost of this? Fi you open and everybody z assigns to 1 I. So this is a distance from I to j. Is that fine? So, but now I, of course, if I show this, then it will be great. So I am going to show that this is less than. Okay, this is at most 2 times this. So of course, which means that this is 2 times the cost, 2 times the weight of the set, because this is exactly equal to 1. So if I less than equal to 2, so I will show this. Okay. Is that fine? Okay, I don't know whether I can. Okay, okay. So suppose we prove this lemma. Are we done with the algorithm? Right. So how did we? So we said okay, fine. All I care about is the I have to care about is the bound on alpha j, summation of alpha j with respect to all the clients. That's all that I care, no? Right. So I'm saying okay, fine. I'll say, look, f alg c alg, right, is equal to summation j in clients alpha j, right, alpha j. Okay. Now remember we had this sigma star and x star, right. So I say this is less than equal to summation I in x star, I in x star. So I am considering particular sets. What is my particular set? I said pick up I in x star, pick up I. So what sets I will consider? I will say pick up f I in x star and set of elements that it covers by sigma star. So this is C sigma star inverse of I. What is sigma star? It is a client to x star. Fix an element. Look at the clients that it serves. Look at that set. You assign that I with that client, right? Another client, another facility, it serves some clients. You take those sets. So now every client is in somewhere, no? So that charge will be counted somewhere, no? That's it. Okay. So this is what I want to write. I in x star okay. So now I define what is Zi. What?
This is you're continuing the why alpha star comma x star.
Sigma star x star is less than equal.
This is nothing to do. This is like based on this I am defining. This is
Okay. Then it is fine.
okay. So what is Zi? Zi is C, client C, and sigma star of C is equal to. So that Zi is those set of clients C in C that has been assigned to the ith facility is Zi. Okay. Zi, right? And what will I now do? I will do D of not even sigma star is required. There have been no I and some j in Z I this. Is that fine?
What is ZI again? Set of
Clients
which is solved by I.
which are solved by I.
Means that inverse function.
Yeah,
Set.
yeah. So this is exactly equal to
Sigma I in star inverse I.
okay. And now what is this less than equal to? Right? What is this? Z in Ji, right? So I can no, this is I wrote something wrong. This is what I want to write. Okay. All I am saying to you, look at the sum of charges. I am summing them up again into different sets. Right? That's it. Because look at this function, right? This is partitions your client set, no? Right? So I'm just I in X star, I'm counting them here with respect to, I said here, 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 here. Right? So J in say is same as J in Z1, Z2. So this is exactly what it is. Is that fine? It is always true. Is that fine or not?
So why it is less than equal to, where is the
Arey, bhai, it's okay. I mean, it doesn't matter. Less than equal to is also equal to.
but equal to is
No, why should I write equal to? No, I want to write less than equal to. That's my wish. I mean, is this a wrong inequality? No, then that's fine, right? Okay. Now, what I know about this? This is summation I in X star, right? Fi plus 2 times, what is this? 2 times summation j in Zi d I comma j. Is that fine? Because of my lemma. For any set Z, this is true. So in particular, it is true about Zi. If I prove this lemma, the sum of charges is not too much than the cost of any set, then this is true. You look very confused.
Yes, I don't understand
What you don't understand?
why that.
Is there not 2 here?
But I don't need to prove, no.
I have.
Okay, okay.
Okay. So this is what it is. If I, this is summation I in X star Fi plus 2 times, okay, 2 times summation sum over, okay, and what is this? This is equal to, what did I wrote? Right? What is this if I take out common? Z in Zi, no, twice summation I in X star summation j in Zi dij. Okay. So this is equal to F star and this is equal to 2 times what is that? C star, where C star is an optimum solution. Because remember or do not remember? CA star was what? Look at the definition, no?
C star is the optimal.
Like optimal cot basis. So we just sum these, this is exactly what it is, no? C star definition, C star. Have you, this is C star. And what is DJ? DJ star is this and this, which is exactly equal to this, this. What? What's your confusion? Can you explain to me?
no, there is no confusion.
Okay. Okay. So this is what will give you factor 2 approximation if we prove this lemma, key lemma, right? And there's nothing happening here. Like in this proof, actually there's absolutely nothing happening here. Okay. But the key proof is how do you relate sum of charges in a set to the cost or the weight of the set. Okay? Okay, so that is what we will spend time on if we are done with this. Look, whatever time happens, I will finish this proof. I am not going to repeat it again. Okay, fine. Okay, so I have told you what charges are, I told you how these charges are defined and everything. Okay, so now all I care about is proving this lemma, that sum of the charges is not too much from the cost of the set. Okay.
Sir, I have a doubt.
Yes, please ask.
The second board, f alpha plus c alpha is summation alpha j. Then after that step, it is less than or equal to the double sigma alpha j, where I belongs to x star and j belongs to z I.
Yes.
So here x star and alpha star are from the optimum solution, right?
What? Yeah, sigma star and x star from the optimum solution. This is from optimum.
When I belongs to x star,
Yes.
That x star, so x star is basically some set of facilities opened by the optimum solution.
That's right.
But that need not be opened by the algorithm's solution.
That's right.
So j belongs to zi.
Yes.
That since that facility is not even opened by the algorithm.
That's right.
How can we consider alpha j for that facility is what I'm not able to understand.
2 plus 2 plus 2 plus 2 plus 2 is less than equal to 2 plus 2 plus 2 plus 2. Do you agree to that?
Yes.
Okay. So what's the difference between this and that? Here are some numbers, which is alpha j, and I am grouping those numbers. What is this alpha j? Here your set of clients, right? Each client has some alpha I. Agree?
Yes.
So summation of alpha is this. Okay. Now what does z in z? What is this z I? It partitions this set into some parts. Okay. And now I sum in each. Will the sum be different?
Some won't be different.
Then what? Then what's the problem here? Then what's the problem?
The j belongs to zi part is what I'm not able to understand. So I.
What do you mean by I do not?
Here exactly.
Oh, like
Zi is the.
what is ZI?
Oh, okay. Oh, zi is the. Oh,
Set of clients that are served by I.
Clients covered by the optimum solution. Okay.
Okay. So, so what is the lemma that I want to prove now? Given I and y, okay, given I, z subset of clients, I want to say that summation j in z alpha j is less than equal to fi plus 2 times summation j in z d I j. This is the lemma which I want to prove. Okay. Okay. Now what I do is the following. let's look at this Z, okay, and let's order these clients. Suppose Z is like say 1, 2, k, okay, okay, and let's believe that, let's for now it doesn't matter, that in like 1 was served before, then 2 was served, then 3rd was served, and okay. So in this order clients are served by the algorithm. Oh, this is bad. Is that fine? Okay. So now basically what I have to do is that, okay, fine, and I also assume that in each iteration also assume that in each iteration we serve one client. Okay, we'll worry about how we will serve. Maybe you first serve 1, 2, then maybe some subset and then subset. I will not worry about. I'll say first I served 1, then in some iteration I serve 2, then in some iteration I serve 3, so on and so forth. But algorithm might serve first some subset, then some subset, and then subset, but I'm not going to do that for now. First, let's assume that each client is served in different iterations, and in this order they are being served. You can reorder them, doesn't matter. Okay? Now we look at the iteration. Now we look at the iteration when j in Z is added to D. So we are looking at the iteration. At this iteration, we are going to add this j in Z to my D. Means in this iteration, the client j is being served. Is that fine? Look at the iteration. I mean, because this is an iterative algorithm, right? So at some point of time, my client j is served. So I'm looking at that iteration. I am trying to understand. At that iteration, what happens to the algorithm? What does algorithm do? What does algorithm do at this point of time? Chooses a facility I, maybe in X. Okay, I'm not. So I'm all the time right. Maybe in X, and what are the chooses? Okay, and secondly, it chooses some y subset of C minus D that it plans to serve. Okay, okay, and of course, J is in Y, because otherwise, how will it serve J? Is that fine? So I'm looking at the iteration when J in this Z is added to D, and I'm saying first. So what does this algorithm does at that point? It chooses a facility I and chooses a subset that it plans to serve, and since it is serving J in this iteration, J must belong to that set, right? Is that fine or not?
So if the facility choose doesn't belong to X, then it also corresponds, it also adds the cost to.
Yeah, so I have not written anything about cost. Okay? Okay. And of course, we have this, at that point of time, we have D, some sigma, right, before we add it. Okay? Okay. So by greediness of algorithm, what can we say? Can I say by greedy choice of my algorithm, alpha j is less than equal to, what is that function? Phi I comma I prime y prime for any other I prime in facility y prime subset of C minus D. Is that fine? Why? Because alpha j is basically this cost, right? Alpha j is the what this guy will pay a charge in this, right? So this alpha j is basically this at that point of time, right? And I'm saying greedy decided to choose I and Y because for any other set, this cost was much more. That's what it says, right? For any other facility I prime, this happens. Is that fine or not? Okay. So this is what is in our hand, right? What is in our hand? That look, boss. At this point of time, this is the only place Greedy makes a choice, no? So at this point of time, Greedy has made some choices, and Greedy had made this choice. Why he has made these choices? Because cost per element for any other choice of facility and any other subset of uncovered client is larger. Is that fine? Otherwise, Greedy should not have chosen. If you believe that Greedy can find this in polynomial time, which we have not going to tell you for now. Okay? Is that fine? Okay. So now what I'm going to do? So this is the only thing that I can infer from the Greedy algorithm. This is the only thing that I can infer, right? But there's one more thing that our algorithm has, that D functions are metric, right? That which I have not used any point of time in the algorithm, right? Like the construction of this algorithm derivative, it says okay, some function D, but I have not used the function is D yet, A. And if I think of a Greedy, this is all that I can say. If you remember set cover, this is all that I could say from the set cover. And from this itself, you have to infer information, right? So if you're making a Greedy, if you have reached at this step, this is all that you have at that point of time. Now, whether you can prove something useful or not, if you can prove something useful, you will get a useful algorithm. If you're not able to prove something useful, then try something else. Okay. Okay. At this stage, I read some primal dual and I have inferred something. So careful. Okay? You understand what I mean? You have to be careful what I say. Okay? Okay. So what I'm saying to you is the following. Okay. So now this happens. This is given thing to me. Right? Now I will say, okay, fine. To get my upper bound, what I needed to bound? I needed to bound upper bound like on this object. I have to somehow understand how the charge of each element which is present in Z is related to each other, right? So I have to understand. So what I'm going to do is that, and all I have is this at this point of time. So I'm going to say, let us find some choices. Let us find some choices of I prime and y prime and try to relate the cost with respect to this by the fact that I did not choose I prime and y prime. Like, so I come up with some choices of I prime. Okay, you did not pick this, which implies that this is how the cost is. Otherwise, you would have picked up that. So this is the kind of arguments that I need to put in my head all the time, right? So I don't know which I prime and y prime is, but there are some canonical ways you can try to play around with it. You understand? Okay. So let's try to understand, okay, what has happened. So if I understand this algorithm, imagine that up to 1, 2, j minus 1 is already present in D. These elements are already present in D. You are making a choice for the jth element. Okay. So let me write the jth element here, j minus 1 element here, right? The last guy that went inside D from Z is j minus 1, j is going, okay? Now, j is going to whom? J is going to some set I, right? J is going to some set I, okay? So, in fact, let's write some L which is strictly less than j. So one possible choice was that, hey, why do I pick map j to I? Why do I not map j where L mapped to, where L was the previous set of elements? That's one possible choice, no? Right? So what I'm saying that, what about the following set? Let's fix y equal to singleton, y equal to j. Valid choice, no? It's a valid choice. And which facility should I map? I say let's, for some L less than j, let the facility be, we know what is the facility that for L less than j, sigma L is the facility that it maps to, right? Why do I not consider why do I not consider my set F right? F, sigma L, and J. This is also potential set, no? Which you did not pick in your algorithm. You understand my point or not? And how do you know that you have not picked? Because J is not yet covered, right? So this also would have considered this set, no? Okay, fine. So why? Because cost per element of this set was much more than whatever I picked because of this. 1 to L is less than J, right? Strictly less than J. So L, so think that L belongs to one of these. So I have a choice, no? Maybe I should have, why am I doing this, right? Okay, why should I not map to J to some previously selected elements, right? So this is one possible choice of scenario, okay? Okay? Okay, so if I think of this way, what can I say this? This implies, because of this, that alpha j is less than equal to what? Why you are not doing this? Alpha, because it's singleton, right? Right? So think of this way, what does tells us? This is very important, that okay, because if I am going to assign it to previously assigned distance, facility need not be open, no? So only thing I need is that cost of assigning y to j, no? Okay, so this is less than equal to d time, what is that? Sigma L j. And this is true about for all L less than, strictly less than j. Do you agree? This I can infer, right? Right? So now, okay. So what does it tells us? That okay, this sum, like the distance from j to anybody else is much higher compared to j mapping to i's, and like that I don't know, j mapping, like whatever he maps per unit cost that he pays from that is less than the distance it goes to anybody else. That's all that I can infer. Okay. Okay. So what can I say now? Okay, fine. So this is the only place that I'm going to use metric property. Okay. So what does this tells us? Now I have, so think of this way, I have sigma L here, I have L here, I have I here, and I have j here. Okay, I have j here. Okay, so what can you say about what about the black distance? Can you say with respect to blue distance? What it be so? This distance is less than this plus this plus this, right? Okay, beautiful. Okay. So I can write that alpha j is less than equal to d times sigma L comma j, which is less than equal to, because of the metric property, this distance is less than equal to what? If I go from here to here. Do you agree to this? Okay, so let's write it down. D comma L plus I plus d of L comma j. Sorry, my bad. I comma j. Is that fine? Is that fine? And this is true about every L less than j, this inequality. So let's sum them all, those inequalities. Okay. So alpha j is less than this for all L less than j. Summing for each L, what will we get? What will we get? How many such inequalities are there? How many such inequalities are there? J minus 1 inequality there. Right? So how many times I'm going to count alpha j? J minus 1 times. Right? Left hand side is fixed. This is less than equal to, now I want to forget this and I want to only write this. Right? So what can I say? My God, it's 12:56, but I'm sorry. I'm not, it's probably class is going to be till 1:30. L less than j. Okay, L less than j. This, right? D sigma L plus sigma L comma. Is that fine? Okay. And what is this? Next is Li, right? And there is Ij. How many times Ij is counted? J minus 1 times. This Dij. Like wherever you go, you will ultimately come use Ij, no? Right? So that is J minus 1 times distance Ij plus summation. What we need now? Okay, I. So L less than J, D, L comma I. Is that fine? Sorry, this is wrong. I comma L. Right? This is also not wrong. Wait, sigma L, L? No, wait. No, wait. Sigma L, J, sigma L to L, I to L, because this is the notation I am using, so my bad. I comma L, and then I comma J. This is fine. Okay? So this is fine, this is fine, this is fine.
This is L, first one, sigma L, L.
Is that correct? No. Yeah, correct. This is fine. This is fine. And what will be this? This will be I comma L. Okay. Is that fine? Okay, so this was one choice. Other choice could have been, okay, because, right, other choice could have been that I map everybody starting from J to K, where? To I. But I did not do that. I assign J to I, no? Maybe I would like to assign all the other guys to, starting from J, everybody else in Z to I, which I did not do. So let me use that fact somehow. Right? So we have another choice. Do we need an algorithm or should I rub this? Should I rub the algorithm? Is it clear to you, algorithm? Why are they making this noise? Of course, I did not tell you how to do it in poly time, which I will do later. Okay. 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 So what is it? So if we this was choice 1, right? This was one potential choice. Okay. This was potential choice. Okay. Here is another potential choice. Okay. So what am I trying to achieve by all this? We are just trying to get some set of inequalities for alpha j, and at the end I want to sum them all, because that is how I want to. Okay. So by doing this, what have I achieved? I have tried to achieve the cost functions. Somehow bring the cost function in the right hand side. That is my whole goal, because otherwise how will I do this? So this is why I am getting all these distances in the left hand side. So I know what I want. I look at what I want from my proof. Based on that, I make selections that gives me something interesting. That's it. There is nothing more happening here. Okay. Okay. So now what are the other potential choice is that I said, haha, let's take y equal to j plus 1 to k, and facility is I. We did not do this, right? Why we did not do this, right? Why did we not do this? We did not do this, right? Because I was assuming at every time you are only getting one element. Okay. So if there is none, then this choice will not happen at all. Imagine for the last guy, this choice will not even happen. You understand? For the last guy, this choice may not even happen for all that you care, right? For the kth guy, okay? But what I know about this, alpha j is less than equal to, what is that? What did we do? If you recall correctly, we said 0 I in x fi, right, plus summation L greater than equal to j, and I am assigning to whom? I to j, and I also need to subtract something, right? Right? And this should be divided by equal to how much? What is the size of y here? I fixed y, no? Because it's k minus j minus 1. So, what do you know? This function is less than equal to 1. Do you agree to this? This function is less than equal to 1? Okay. So, I will not bother about this for the upper bound. Understand? I will not bother about this for the upper bound. Like I will just forget this and keep fi. Okay? So, now if I take this common here into here, what can I write? K minus j plus 1 alpha j, I forget 0. It is fi, right? I am only drawing upper bound, right? Is that fine? It should be? I didn't get. What are you saying? You're right. This is like. Okay. Now let's try to understand this quantity a little bit. Okay. Okay. What can be come up with a lower bound on delta di? Imagine that you are assigning first I minus 1 guys to I, because first I minus 1, first j minus I guy has already gone inside D, no? So, they can be reassigned to I, right? So, what it will be? So, that is the cost of D times, if I assign them, then it is sigma L, right? L, right? This is what they were paying before. Now, what will they pay? I comma, what will they pay? Is that fine? So, I claim that this is at least this much. Think, you know, but look, what is it? That's positive quantity. That's negative quantity, only, no? Look at this quantity, right? What is this? If already assigned guy is good, then this is negative quantity, right? So, that's contributing, if that was contributing 0 here, you are contributing negative here. So, that's greater, no? You agree or not? And if this quantity is, okay, so, but yeah, and if this quantity is smaller, then you are anyway contributing positively or contributing positively now. Look, either this is bigger or not bigger. If this is bigger, then in the D also in this also you were contributing, but if it is not, you are contributing 0, you are contributing negative. So that's fine. Okay. Okay. So from here, what can we write? Right? From here, what can we put it here? Okay. So this guy is at least this much, right? This guy, so what I can say, this is less than equal to, so if I put this here, you understand, right? Because you get my point or not? Because this can only be more, cannot be smaller. So if you subtract something more, this quantity is only smaller, right? Right? So then I can write this as Fi plus summation L less than J TIL, okay? Okay. So what is this? Okay. So this will become plus, right? For all L less than equal to J, right? So what can I write? L in Z. Because if I put this quantity here, minus minus will plus become, and it is distance from L to I, L less than J will come from here, L at least J. So L in Z or L less than equal to K I can write here. Okay? Okay. Now minus this quantity, right? Is that fine? Until unless I made some stupid mistake. Okay? So this is my first set of inequalities. This is my second set of inequalities that I got on this. Okay? So all this is about upper bounding alpha j's, right? All this is about bounding, upper bounding alpha j. So now if I, so alpha j is bounded like this, alpha j is bounded like this. So if I sum 1 and 2, what I will get? Is this fine with you? Is this inequality fine? Huh? So what is not fine? This lower bound. Why this? What is the definition of this? For every client, what happens? Maximum decrease. What we wrote? Max of 0 comma this. Is that fine? Okay. So suppose this is positive. Like this is larger, then this quantity is anyway counted here. So at least this one. But look at the quantities where you do not want to be reassigned. What is this number?
So maximum reassignment, maximum number of reassignment is.
What is the definition of delta? Look, first of all,
Good or bad?
what? Delta di has a formula.
Yes, I know.
If you look at that formula, it means nothing. It means that I'm just trying to get a lower bound on delta di, right? I'm saying, look, if you don't reassign me, then it's fine, it's okay. Then it's only negative. This computation is only negative. Okay. So thinking more is not helpful here. Okay. So let's do this. So what will you get? K times alpha j is less than equal to what? Huh? First of all, Fi plus plus this quantity, right? Okay. Let's call this quantity diz. It's like for every z in j. This is what I mean, the L less than, okay? Just otherwise it becomes too cumbersome to write. So what I can say? D, every element in I, every element in Z has been assigned to I. That's all that it means. Okay. And this is the sentence can be, and there is also this, right. So, is there something that we will? Okay. So, Fi plus Diz, then we have this, right. What is this plus, right? J minus I. Okay, I don't think I need this anymore. Plus what is that? I. Okay. So how many terms have taken care of? Some things are not getting cancelled. Which got term cancelled? This, right? And this term will get cancelled, right? This term will get cancelled. Great. So what is the last term remaining? This one. So plus summation L less than J D I L. This is what we got. But what were we interested in? Summation of alpha j. Right. So let's get this. Okay. So if I have to do so sum over alpha j, j less than or equal to k. I am summing over all this. So what it will be? What it will be? Huh? What will be the here? Tell me. K times Fi. Okay. Okay. K times Diz. Okay. K times these two quantity. Is that fine? Okay. Can I write this plus k times j minus 1 Dij is that? Yeah, j will change, no? This is not what it is. Okay. So this is going to be, I think, it is j minus 1 Dij, right, with respect to j, right. So I can say this j less than equal to k, right, j minus 1 Dij. Is that fine? This also will change, will it? Right? L is less than j, right? So summation, what will I say? Say I equal to 1 to k, right? And now if I have taken I, it should be Is it making sense? Or j equal to 1 to k? It should be this, right? And then L less than j d I comma L. Does this make sense? Okay. If I divide by k everywhere, which I need to do, so then I will get this is less than equal to Fi plus Diz. Are we starting to get something interesting now? Right? We got Fi, right? So we got Fi. Now what was that? This is Diz, which is basically this 1, and the rest is rest. Okay. So this I should be able to bound it by another thing. Okay. So this is summation j less than equal to k, j minus 1 Dij. This is basically, if you notice, this is dz what, okay, okay, fine, and plus summation j equal to 1 to k L less than j dil, right, this divided by k. Okay. What is this quantity? Let us try to understand this. I do not understand, but let us try to understand this. Sorry, it is taking time, but I cannot rush. Okay. Okay. Let us try to understand this. Okay. What is this? Okay. Let us ask ourselves, look at a quantity dij, right? Look at, so everybody is assigning to I. Do you agree? Now let us assign how many times a client j is counted. Okay. So here look at assignment I and this is my client j. In this formula, how many times is counted here? J minus 1 times? Okay, excellent. And in this formula, how many times is counted? K times. L less than j. J minus. No.
Because it is the strictly left.
J equal to 1 to k.
Okay, and A less that means
When will he count it? Only for, only, look, if I am a j here, when I will be counted? I will be counted for people above me, no? Look at this. Will you count me for below? Right? So j, no. So yeah, so I shouldn't say x, some x, okay? So it's, how many times this x is counted? X client, j minus 1 time? I shouldn't, no, this is j is j, okay? I should have written here, is this making sense? No, wait. No, we have to be very careful. Here, what I was assigning to? ith facility, right? What I meant is that, okay, imagine the, why were I assigning it to I? Because jth guy was assigned to ith guy. Okay, no, fine. No, all I am saying to you, look at this. Okay, so this is like, let us say I equal, not I, use some different variable, okay? This is why it is confusing. So tell me some other variable. P equal to 1 to k, L less than P, okay? P equal to 1 to k less, okay. Now you have fixed the client j. When will he count it? When P becomes equal to j plus 1. Look at this sum, no? Look at P equal to 1, P equal to 2, who will be counted here? First, di1. P equal to 2, P equal to 3, di1 and di2 because L is less than P. So how many times, so if I want to count a j, contribution dij, then my P has to be equal to j plus 1, j plus 2, ... k. So what is this quantity? What is this? So how many times dij is counted? J minus 1 times plus k times k minus j time from here. Yes or no? Look at dij, right? When is dij counted here? Imagine the j is 5. J is 5. Can, for p equal to 4, will this be counted? Can, say, if I p equal to 1, will this will be counted? 2, it will be counted. 3, no, 4. So, but it will be counted for every p greater than or equal to strictly. So, 6, 7, 8, 9, 10, up to k it will be counted. So, this way, right? So, if it is, it will be counted for k minus j times, right. Okay. So, what is this quantity? What is this quantity? This quantity is nothing but k minus 1 times d I z. That is all that I am saying, right, because each distance for an element in z is counted k minus 1 times. This is exactly equal. This is not even, right, this is not even nothing, this is exactly equal to this. So, what I got now, right? Okay. So, this is Fi, this is Diz, and what is this? It is k minus 1 times Diz. If you divide by k, it is not less than equal to Diz. It is, no? Right? Then we are done, right? This is what we wanted to show. Anyway. Okay? So, the case when each element appears in different round, and you can show that even if they are bunched, this is the worst case, because when they are bunched, they pay lesser price at that point of time. Okay. So, next time I will tell you why we can do that selection in polynomial time. Okay. So, this is a factor 2 approximation, and this is from, if you really are interested. So, actually if you work hard, this is actually not factor 2 approximation. Okay. If you really work hard, this is 1.61. Okay, but that is beyond me. I mean, I cannot really. This is okay. So, this is a paper by, okay, it's called Greedy. If you are interested, Greedy Facility Location Algorithm. Greedy Facility Location Algorithm. Algorithms analyzed using dual fitting with factor revealing LP. Journal of ACM 56 795 to 824 2000.